Okay, we have so far covered the predator-prey model, and before we start the epidemic model, we will review what we have done over a month. Okay, first I have uploaded some of the population model and epidemic model files, and also I have uploaded a file that that we may talk today, which will be a mathematical, simple mathematical problems on optimization problems and Newton's method today. And also, I have uploaded an app, Android smartphone application, Math in Seoul, so you may find it from Google Play Market. So, which Mr. Hwang Seung-yeon helped us to finalize it. And today, we're going to talk on mathematical modeling and optimization, and also I'll give you a chance to share your March PBL report in the following order. And Mr. Kim Mo, Hilden, and Sun Xiaowei, and Mr. Hwang, and Mr. Hong, and Jun, and Mr. Lee Jae-un, Yun, etc. Today. Okay. And also there are lots of discussions today on what? On the problems that we have covered on Monday. So first, I gave one reference on bifurcation. So here in the meaning of the bifurcation is in differential equation. If you understand the situation, all we can do is to analyze the behavior of the solution to understand it. So we have to think how the solution behaves. It can be a stable solution to reach the equilibrium point, or it may occur, or it may reach an unstable status. At that point, the place where something divides into two branches of the solution, we call it a bifurcation point. So as we mentioned in the last class, bifurcation is the situation that bifurcation occurs when a small smooth change made to the parameter value of the system causes a sudden qualitative or topological changes in the behavior. That's what I meant. And Mr. Lee Dong-gil talked about the predator-prey model. He added an Excel file that simulates the predator-prey model, and he tried to add hunter with a certain restriction. And he asked the situation that was occurred in the file, and Mr. Chang asked that she couldn't find the situation that Mr. Dong-gil Lee raised from the given file. So I asked Mr. Dong-gil Lee again to explain more on the situation can be represented in the Excel file. And Mr. Lee uploaded the revised version of the file, and that says that with the all the situations and the conditions that he tried to adopt in this Excel file. So I will give him a chance to explain what he did. And also, I talked from the last lecture that we had. I asked one of you to fill out the spot that I left for you to do for formulation of the equations that I showed you. So Mr. Jae-yoon Lee and added his explanation to the given informations that I have delivered. So here, he will talk a little more on what he found in the process of understanding the equations. So I will give a chance to Mr. Dong-gil Lee and Jae-yoon Lee to explain on what they did. And also Mr. Hong Seok-jun raised a question on the rabbit population model, it was the simple question which is finalized. So when you finish it up, when you got the answers that you wanted to have, then you may just add the final note in the title of your comment. So we may go back to those questions which has been clarified in Q&A. And also Mr. Kim Jun-sung mentioned on the Jacobian symbol algorithm, which he learned from cryptography class, and he raised the question that he faced a difficulty on it, and Mr. Hong Seok-jun and added his questions on it, his answers on it. And also Do Myung-lee raised a question on simulating a situation in SAGE for the rational numbers, and Mr. Hwang Seung-yeon tried to give an answer on it. And so, and also Jae-yoon Lee added what he did on SAGE, which is a very early practice on adding numbers and finding the factorials, and just simple computations in the early stage. And also Jae-yoon Lee tried to solve a problem, homework problems on extended logistic growth model, and Mr. Hwang Seung-yeon and Jae-yoon Lee discussed on it to finalize those questions. And also, some discussions are going on problems in chapter 13 on mathematical modeling, on graph theory, and there was other simple technical problems which was raised, and the solutions were given. And also Do Myung-lee tried to practice on power method with Excel, and his difficulty was solved to by Mr. Hwang Seung-yeon, and also Mr. Jang Ji-eun added an explanation of this power method in detail, so you can refer that. And also, I raised, I posted a newspaper article recent, and which is pretty much related to what we are doing in our class. Okay, and also, Mr. Do Myung-lee raised a question on mathematical modeling and statistical physics, and he must cleared up his question with the answer by Mr. Jun-sung Kim. And here is the answer. And for the power method, when you're trying to find the case power of a given matrix, instead of just coding all the process, you may use a macro that replace a previous power to make the next one in this way. That solves his question. So Dong-gil understand it, and Do Myung-lee also find it. And also I have raised other questions here. The Miss Ji-eun Chang and raised the question, added question. I added an explanation on the power method, which from the textbook of mine, and she summarized in an easy way. So you can take a look. So finding the largest eigenvalue numerically, what you have to do is finding the lambda and non-zero vector x that satisfies this equation. So suppose you have a non-negative matrix with distinct eigenvalues, then you have n linearly independent eigenvectors, which forms a basis for the n-dimensional vector space. So any vector x can be written as a linear combination of those eigenvectors. So replace x by that, by this. So you have this. If we choose the largest eigenvalue lambda 1, which is the algebraic multiplicity 1, then naturally you can find the relationship like this. From here you will find this lambda I over lambda 1 all converge to 0 as k goes to infinity, except the lambda 1 over lambda 1. So since all others goes to 0, so at some point you will have these relationships. From here you can find the largest eigenvalue lambda 1 and corresponding eigenvector v1, and this is how we find the largest eigenvalue and its corresponding eigenvectors, which is called the power method. And she summarized it well, so it will help you. And also, I have uploaded an application of an epidemic model on H1N1 virus, virus, and a paper that you can find from here, and also one Excel file that produced this article was attached. So you shouldn't have any problems to understand it. Here, you will find the mathematical modeling of the H1N1 influenza, which the mathematical modeling technique that was covered in our class was used to draw the simulation and possible conclusions on it. And an Excel file of those situations for H1N1 virus and was simulated with the data from National Statistical Portal site and National Institute of Disease Control, and those are the situation. So you will find it some informations that you can utilize from what we are learning in here. So today we're going to start with the mathematical modeling on optimization problems, which is a very basic things that shows how you solve the real life problems with the techniques. So on those problems, all we have to concern is formulate the mathematical equations from the given condition. And so before we start, is there any questions? Okay, optimization problems. Okay, here we study to find the extreme values. For practical problems. Okay, so for example, in business, we want to minimize cost and maximize profit. So in real life problems, we should convert the real world problem into a mathematical optimization problems. And here are some guidelines for solving optimization problems. First, we have to understand the problem first. Then we draw a picture with variables. The first introduce a variable to represent the quantity to be maximized or minimized. Okay. For example, A for area, V for volume, H for height, and T for times. And then we may draw a picture that include these variables. Okay, to understand the situation. Then express the quantity as a function. So to form a simplified mathematical form. So if the functions is of more than one variable, then use a mathematical ideas or given conditions to obtain a function with one variable at this first level of the optimization problems. And also you have to consider the domain of the function. Then determine the absolute maximum or minimum values of a function to deal with the critical point and critical situations that may give an answer for maximizing profit or minimizing the cost. And finally, we have to interpret our solutions obtained in the context of the original problems. And that's the step. For example, if we have a waterway that has the water passes to be made so that its cross section is a trapezoid with equally sloping side, the theta angle. The width and two sides of the waterways are of the same length, equal to 5 meters. So this is 5 meter, and this is 5 meter, and this is 5 meter. So how should the sloping angle theta be chosen so that the waterway carries a maximum amount of water? So we want to maximize the volume of the water that passes through this waterway. So we need to formulate an equation. So let's draw the graph of it. So we have a waterway like this. So this area and this area are same because the zetas are equal. So we may move this triangle to here to make a rectangle. Then we want to maximize this volume. So the volume of this this rectangle is the base times height. So base is 5 plus 5 cosine theta, and height is 5 times the sine theta. That's the height. 5 times height. So we have 5 sine theta times the base 5 times 5 cosine theta. So we have 25 sine theta times 1 plus cosine theta with a single variable theta. So our goal is to find a value of theta that maximizes A of theta. So all we need to is to find the critical point of the volume, the area of this canal at a certain point. So let's find the first derivative of it, which is this, and then solve the equation, which is a prime of theta is equal to 0 to find the cosine theta is equal to 1/2, yeah, or on the 0, but 0 is not in the domain, so 0 is a critical point number that does not make physical sense in the context of the problem. So we have only theta is equal to 3 over pi, which can be simulated in this way. So if we go to this to draw the situation. Okay. Then anyway, yeah. So yeah, we've been through it. So as you see, yeah, there are several problems which related on optimization problems. So from those given situations, all you need to is to form the reasonable formulation of the situation, and then use the differential and integral the calculus to find the critical point and the extreme values to solve it. Here you may use the website that I already have coded. So if you use some of those commands from this website to deal with the other problems as well. So the things are like what you see here. If you form an equation, then you can easily draw the graph of it. And also you can easily find the derivatives of that function, and you can draw the graph of it. You can graph of the equations Q, and which is a dotted line like this, and then you will see there is a critical point at near 5.5 here, which will be this, and you can easily use the computer algebra system to find the approximated value of those point as well as the optimal solutions which was asked. So if you use those now everybody can use such computational tools. The mathematical modeling part are getting more important. So what you are learning is in this class is the part of mathematical modeling from the given situations. So I expect some of you may try some of the other problems to form an equation and use the code that I have provided to cover to find the solutions from the given one. And also this Newton's method, so section 4.5. Okay. I will introduce Newton's method for you. Suppose you have a linear equation like this or quadratic equation like this, then you can easily find the solution from the formulas. But if you have the equation of degree 5 or greater, then you don't have a formula, so you have to find the other ways. Okay, so if there is no exact formula for solving the f of x is equal to 0, then we should turn to numerical technique. And this Newton's method is based on the idea of a linear approximation, which works very well. Okay, so here is a procedure for Newton's method that finding the equation of the tangent line L at the point x1 f of x1. So at that point you have a derivative f prime of x1 that passes through x1 and f of x1. So this is the equation of the tangent line that passes through this point of the function f of x. Then solve this equation. Then you have what? So when y is equal to 0 means that's the point that this equation passes through the x-axis, which means it's a solution. So let y is equal to 0, then if f prime of x1 is not 0, then we have x2. You can find x2 which satisfies this equation. So as you see, this is a very interesting formula here. So after that, if we can also find the tangent line at over f at x point x2 f of x2 in a similar way. Okay, so with a similar situation, give x2 here and x3 here when y is equal to 0, then we can have a same equation with x2 and x3 like this. We continue this process, obtain a sequence of approximation x1, x2, x3, as you see in the graph. So you start from x1 here, find the tangent line. Then the point that passes through the x-axis, let that point be x2. Then find the point x2, f of x2, and find the tangent line again to find the x3, and use the x3 f, the point x3 f of x3 to find the tangent line at that point to find the point x4, so like that. As you see, this point approaches to a certain point that if it converges, that usually the solution that we are really looking for of the function. So the number xn become closer and closer to a solution if the sequence xn converges here. We may we may compute the third approximation. So find the x1, x2, and x3. Then of the equation x4, x to the fourth minus 7x plus 1 is equal to 0, starting with x1 is equal to 2. Then apply Newton's method on this. So f prime of x is like this. So choose x1 is equal to 2 to find the x2, which is 1.88. So we start from x1 is equal to 2, find the slope, the tangent line that passes through here. As you see, that first point x2 passes through 1.88. And do the same thing to find the x3 on the same equations, to find 1.8630. And so you have x1 and x2 and x3 like that. That's what it was asked to. As you can easily expect that number approaches to a real solution like this. We may simulate it in the formula like this, and then we can. So if we have the equation here at x to the fourth minus x7 plus 1, x to the fourth minus what? 7x minus plus 1. Okay, plus 1 like this, and then we can we can find x to the fourth, and as you see, if we start from what, from point 2, and then we can easily find the x. If we start from here and find the x1 and x2 and x3, we can easily see the point approaches to here. So here CPU times and everything here. Root is 1.86, and the it converts to root the 1.88 after first iterations. If you change the function and starting point, and if you change the error bound, and we can also control the intervals to do all the simulation. We can do the sine x here to the so we basically we can do we can put we can add any functions here to draw the graph, and finding the root of the given equations with the destined error bound that we can control. All this simulation can be done with this code. So you can even change the code here to deal with this. And also, if you have questions on it, there is a manual is inside of this cells that I will explain it later after you have a little bit of practice. Okay. Anyway, so that Newton's method also can be used to find the approximated value of any numbers. So finding the fifth root of 40, then you can set y is equal to fifth root of 40, and x is equal to, then x to the fifth is minus 40 is equal to 0. So you find the solution of x to the fifth minus 40 is equal to 0. So you can use the Newton's method on this function to find the sequence of solutions. One important thing is you need to start from a reasonable distance from the approximated the solution. So important thing is you better draw the graph first and start from a reasonable point near the solutions to get the quick answer from it. So all those things can be simulated in here and here. So you may use it. So that's what I showed you. So before you had to find it with this computation by hand. Now you don't have to do it since you have already pre-coded software to deal with it. So now you have the computational tool to deal with the solving the equations and draw the graphs of the equations. So what we need now is a mathematical formulation from the given situations. That's what we are learning. Okay. So I think now it's time that you can talk about your work. So now, we will have some of you's March PBL report. So we will share the experience that you have had over the last month. Okay. Kimmosa, I think this is Kim Hild. Okay.
Okay. Let's see. I just skip this part and I don't need to explain this. No. Okay. My first work was the Fibonacci numbers. This is quite similar to the problems what was in the class material. It's the same model that was on the material, but I just wanted to do it myself, so there it is. Blah blah blah. And this is the annuity problem I told you about a few weeks ago. And here's the code. On this, but I told you last time before, yeah. So it's the one I told you about. Yeah. Here's the pictures of that program. And this is the overshoot and collapse problem. This is the last job I have done. And there was something in the Excel book about this overshoot and collapse problem. No. First, here is the exponential growth equation, and then the logistic growth here. And I found this quite interesting case about modeling the real life deer population equation, deer population in each year. And there's many different kind of loopbacks to the actual deer population, and everything affects every other thing, like this. And this is my very simple equation model about the overshoot and collapse. And here the death rate is actually only dependent of the food.
Where did you find those 3% of graphs?
This one, you mean? Okay, here is the. This is the hyperlink. Yeah. Okay, so you can, if you want, you can see it here. So yeah, the death rate is dependent of the food, and as you can see, when the food runs out, the death rate reaches 1. So this happens to the population at that point. And I wanna extend my model with something like this later on. And that was all. Okay, thanks.
Yeah, next.
Hello everyone. Yeah, now I will talk about the PBL report. Yeah, first is I revised some model SIS models which sold by Idongi, and he takes some mistakes, and I give some the right models and right codes, and there's some small mistakes, such as he put the nodes inside of the functions, and others are missing the marks and so on. And there's small things, and he did the main functions, and there for March, what I have did in the March, and the first is a course model, and and it's simple, and there's the induction for a model, and everyone knows these models. So really it's a relationship by this, and I published it in there. Yeah, it's simple models. And followed and the Fibonacci numbers in integers. And in the class, and the professor that just for the positive integers, and then there's negatives for the Fibonacci numbers, and we can, as we mentioned in the class, and we can get the matrix and get eigenvalues, and there will be a there was a large eigenvalues in there, and the smaller eigenvalues in there, and which is in here.
So you have dealt with the generalized Fibonacci sequences.
Yeah. And the second and the third is the generalized Fibonacci sequence, and we will do in the similar ways, and find the eigenvalues, and we know and its numbers will be relations of the relations will be the eigenvalues similar. And thus and the following is the biological models, and actually it's something similar with the generalized Fibonacci sequence, and I have did the analysis in there. And also for planes, it's the generalized Fibonacci sequence, and so we can find the seed over plane, and we'll get these numbers. And I checked it, and it's really it. And the following is the logistic growth models.
So did you try to make a scroll bar to control, to simulate it?
Yeah.
Okay.
Here I give the questions and the analysis. And
Okay. Yes. Yeah.
Yeah.
So yeah, you can really simulate.
Yeah. We can change the numbers.
All the variables are changed.
Yeah. And I give the how many of the variables and in here, and you can check. And
okay. And also I may add one hint for you. So when you need command, when you need to know a command here, for example, just make a question mark here and just evaluate it. Okay. For example, for n, if you just make any first word on the command and with the question mark and evaluate it, then you will have all those the pre-coded the command or the manuals on it like this. Okay, for example, factorial or fact f or question, then you will see all fact f a c what else, integral. Then you will find the command like this. So whatever differentiation. Okay, if you need to know any more manual, and the manuals are already in here. All you have to do is just type a few word there, and with the question mark and do evaluate it. Then you will have all the manuals. So you have all the information in it. Also, if you type, if you click here, 여기서 저걸 주려면 어떻게 주지? 여기다가 if you want to type some command like this, then all you have to do is just with the shift key and click this, then you will have the notebook here. So you can find here is my explanation on whatever. So you can type all those mathematical simulations or whatever. So here you can type math symbols and whatever explanations with the code in it. So you can really make a web page easily here to publish it with your explanation and your code and your simulations and your graphs and all together. So so it's all supplied in here. So that will help you. Okay, you may continue. 하나에다가 모든 설명까지 집어넣고 굉장히 편리하게 거치면 되지 않습니까? 퍼블리시한 다음에 다른 사람들 설명을 뭐라고 링크만 주면 되고 퍼블리시에 있는 걸 카피해서 그냥 QL에 주면 그냥 클릭 왔다 갔다 안 해요.
Yeah, and following is the logistic growth model, and it's based with the extend growth model, and just change the growth rate by this. And in here we can see the Sage code. Yeah.
So you have all the information there with the web addresses and the files. So you just go through what you need to practice. So to do whatever you like to do in mathematical modeling class.
Yeah. First, just some relationship about them and I record in here, and then from.
As you see, do it once again. But
yeah.
As you see here, if you type it, then what you have is all the text code there. So if you just type it, then it will be saved with a LaTeX code like this. So you don't have to type LaTeX code like the others do it. Just you type the equations or word there, then it will make you kind of the paper format in math and physics. So writing the papers with this, that will save you lots of time too. 저기 치는 세이프가 되기 전에 코드를 저장해서 그러니까 바로 텍스트 코드로 옮겨서 논문 특별히 그냥 끼워넣고 쓰는 거니까 집어하는 것들이 다
By the analysis, and I finally I find some relationship about them. There get some calculations, and there's animals increase faster and faster until the number of them reaches half of the capacity, and animals increase over time until the number of them reaches the capacity. And also there's for the when case equal to 1, and there's the extend growth model, and there's case not equal 1, and it's bigger than 0, and we can get some similar calculations about the extended growth models. And let's follow.
Why don't you go directly to the conclusion?
Yeah. So, and about the power method, I just find the largest number, and in the code we can see the m, and we just change the m, and we can get the m by m matrix. And
yeah. So you have seen the Excel file to deal with the power method. It's by making a macro code on the matrix in Excel is not easy. It takes a lot of time. But as you see, the Sage code makes it much simpler and much powerful. So better use this Sage code instead of Excel on the mathematical computation.
Yeah, and if we put the large numbers of k, and we can get the number more and more similar than the real eigen values.
Change the number of size by 4. Here, by 4. No. Yeah. Change the size of the matrix for random matrix. And you will have the 4 by 4.
Yeah.
If you change the number, you will 5 by 5. So in Excel, you cannot do it. So, but here, with the very simple code, yeah, you can generate the whatever you like to do. So it's very powerful.
Yeah. 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 And there's following is the SEIR model and the SIR model.
Okay,
with
I will give you a chance later on those epidemic models. Since the times are almost up, yeah, why don't you go to the conclusion today? 결론. 제 PBL 보고서의 결론이었어. Okay.
Yeah.
You may.
By taking the class, and I learned the method how to set up the models with it, and to take some analysis with the sage, and and change them into some mathematical language like the matrix and the functions, and that's all I have learned for this.
Okay. Thank you. I think we have learned what other students have done it. So since time's up, I will close up today's lectures and we will continue. I will give you more chance to talk on what you did in next week's class. So if you have any question, feel free to ask me now.